So we'll go through today and so chapter 3. This is circuit analysis techniques. And in this chapter, we will get node voltage, we'll get mesh current, and we'll talk about linearity properties very quickly, and then we'll do Thevenin and Norton, and then maximum power transfer. Okay. So if you, in your past, did not learn about how to do node analysis, we're going to cover it really quickly. So the node analysis approach is to find the unknown voltage nodes. Okay? And then we write current equations, current Kirchhoff current law, KCL, at those nodes. And we're going to do some example problems at the end of the chapter in order to do that. I'm not going to do these example problems, even though I'm going to go through them. I'm going to show you where they're at, and you can look at the you can look at this part of it, and you can stop the video and look at any of this part that you might be interested in. But we're just going to work problems at the end of the chapter today. So this is where there's an unknown voltage or where there's an unknown node, you can write a current equation at that node. This is examples from the book. You should have done this in resistive circuits. So this is basically a review of resistive circuits. Okay. Here's an example. You find the unknown nodes, VA, VB, and VC. You write current equations at those nodes. So the current coming in is equal to the current going out. I0 minus I1 minus I2 equals 0. So the current going into that node is equal to the current going out, but you write it in terms of voltage. Okay. And in this case, we have three equations, three unknowns, and we'll talk about how to solve that. That's a determinant. We solve them as a determinant. We solve that as a determinant. Here's one with two nodes. We can solve that one as well. So again, you in your test time, you can bring some crib sheets with you, and if you forget how to do a determinant, I'll go through it today again, but you should be able to know how to go through and evaluate a determinant, a 2x2 or a 3x3. That's the other part of this course, and we talked about it some in resistive and reactive circuits, but again, it's something they need to brush up on. Here's another one. Now, sometimes you have a current source. at which time that's like a constant going in. In that case, you just write it, there's my I source. So I've got about 8 problems in the chapter we'll go through, and we're reviewing the chapter now, just kind of reviewing it, and at the end of well, when we get to the problems at the end, I'll basically just work 8 problems. We may not get through all 8 today. So this solution is called Cramer's rule, and we'll talk about how Cramer's rule works, and I'll explain it again to you. It's not hard. It's the easiest way to find 3 unknowns, 3 equations, 3 unknowns, to find each of the unknowns. It's the easiest way to do it. Here it is in the book. You never do this in the real world. You use MATLAB or something like that if you're interested in doing this. But for a test, you've got to do it yourself. And if you take the PE test, you have to do it with executing a Cramer's rule. They never go bigger than 3 by 3, but you could expect a 3 by 3 on the PE test. So that's kind of a given. They don't go to 4 by 4 or 5 by 5, but they do expect you to be able to solve a 3 by 3 on a professional engineering test. And I know you say, well, that's 8 years away. I don't even want to I don't even want to think about what I'm going to be doing 8 years from now. But you might. Or, like I said, if you do your master's degree, it'll be 3 years after your master's degree. So you might be able to get it quicker if you go ahead and get a master's degree. And you can get a master's degree here at night. You don't have to be you don't have to do it at full time. You can do it at night, which is the way I did it. Got a master's degree at night. So anyway, I want to bore you, but since some of you did not buy the book, I do want you to know that you can stop this video and read at your leisure. All right? It can sometimes be referred to as scanning a book into a video. There's a 4 by 4, and you do not analyze a 4 by 4 by the same exercise you do a 3 by 3. It's a little bit more difficult. But again, they just say use Multisim or MATLAB, and it'll do it for you, and that's true. I could show you how to do a 4 by 4, but I don't think it's worth it. I don't think you'll ever see a 4 by 4 done by hand. So again, you're going to be asked at some point in your life, if you want to get a PE, to do a 3 by 3 by hand without benefit of a calculator that can do it. You have to do it with a $20 calculator, not an expensive calculator, but you can do it. It's not hard. Okay. Moving along. That's a summary of node voltage analysis. Mesh. This is the one that everybody, I hate to use the word everybody uses, but this is the common one that most people use to do an analysis. Mesh. And that's a little bit extreme, but in that case you have 9 unknowns. So each current is going clockwise in its own little sphere, and there's 9 of them. Where they meet, it's U minus the other one. So it's here, if you're writing the one for IF, it's IF minus IJ times M. Here it would be IF minus IE times that guy right there. It's where you meet somebody else, it's U minus the other one. Very straightforward, very easy. But then I say that, and then you get 3 equations and 3 unknowns out of it very quickly. This gives you 3 equations and 3 unknowns. Okay? This IA, IB, and IC. In this case, IC is I6. IA is I1. IC is, or excuse me, I2 is IA minus IC. So that you have to sometimes go back at the end of the problem and find the actual answer. So that's I hate to say it, but you close your eyes, you turn the crank, and away you go. And this is typically how problems like this are solved, is with mesh. Why is mesh easier than node? Because you do not have to deal with messy denominators. Node, you have to deal with messy denominators. Mesh, you do not. So it's a much better, much easier approach than node. Okay, mesh analysis. Here's an example. Solution. Another one. Going too fast, everybody? I know I'm going too fast. Basically, I'm going through this so that you could have some reference if you want to go back to. And I'm no way discouraging you from buying the book, but I understand if you don't. This is a way of having some reference to go back to. The main thing here is the problems, and we're going to go through 8 of them today. If you can work if you can work these 8 problems, you can work anything from this chapter as far as I'm concerned. Linearity. Everything in this whole book is linear circuits. In other words, it works the same way in the positive direction as it works in the negative direction. If you have a diode, not linear. So if you throw diodes into this chapter or whatever, all of a sudden these equations go to pot. Okay. Now they do talk about Thevenin and Norton in this chapter, as well as maximum power dissipation. So they ask you to be able to do those as well. And this is still a linear section. Superposition, additive property. Very rarely used. There's superposition. If you want to hear this from the lady speaking in AI language, I'll turn it on if you want to listen to her. You want to listen to her?
Chapter 3 Circuit Analysis Techniques. Assuming any system of linear conductors connected in such a...
There she goes. There it is, the voice of the lady who is doing this. Okay, let's go back. I should have known that it jumped to the front of the chapter. I didn't want to do that, but that's just the fun of it all. There it is. If you don't want me teaching it, you can have her. So if you vote for her, you can. Anyway. This is called speed reading. I think we're back to about where we were. Anyway, so Thevenin. Thevenize everything before your eyes. Okay, so this talks about Thevenin and Norton. And the other day we talked about flipping back and forth between the two. Okay, so exercise, there's one right there. So basically, this guy tells you can Thevenize anywhere in a circuit. You don't have to Thevenize at the right. You can Thevenize on the left. You can Thevenize in the middle. And one of the example problems that we have, Thevenize is right in the middle of a circuit, so we have to be able to do that. And we follow the rules, and the rules are very explicit. I'll go through those. When he says find the Norton, I always find the Thevenin and then convert to Norton. I always go for Thevenin. I never use Norton. I think it's too confusing. But anyway, I very rarely use Norton. I use Thevenin. And this is the proof of Thevenin. Very rarely do we prove things in this course, but there was the proof of Thevenin. So again, it was something that I never hardly ever even thought about until I got into teaching. And then in engineering technology, they talk about Thevenin a lot. In engineering courses, it's always mesh analysis. But the reason for Thevenin is the Lego approach to building things. So you build things from Legos, everything kind of fits together. And if you look at things from a Thevenin point of view, it does make good sense that you look at it from a Lego type approach. And it's very, very appropriate, and it makes good sense. We're always talking about the input voltage, the input resistance of a circuit, the output resistance, that type of thing. And all it is the Thevenin equivalent, or Thevenin. Maximum signal transfer. When RL is equal to RT, you get the maximum power out. Everybody remember that, right? Any questions about that? And it talks about interface circuit design, and I'm going to go through that very quickly, and then we get to the problems. So we're going through this rather quickly. We may not get through all these problems today. I don't care. We'll pick up where we left off. A lot of interesting things in this book. It's a very, very good book. I mean, it's not like you got to buy it, but it's just a good book. A lot of stuff. Okay, we're down to number three. So we're going to work today through a number of problems, and hopefully we get through some of them. And if you are so inclined, work along with me because I have not worked these already. And we'll get through them together, okay? So I'm going to try to do 3, 3, 3, 4, and these are your assignments. 3, 3, 3, 4, 3, 9, 3, 11, 320, 341, 358, and 361. Okay, so those are the ones we're going to try to work on. This is 3, 3. So write the equations for this. So it's a VA and a VB. So you have two unknown nodes. You have VA and VB, right? What is the current? Okay, so you have a node VA, you have 40 milliamps going that way. And this way you have coming in, you have 20 milliamps. And this way you have something, an unknown, and this way you have an unknown as well. So how would you write that? VA. Well, the current going to the right is VA minus VB over 3K. So that's the current going to the right. The current going down is VA over 1.5K. And the current going this way is plus 40 milliamps. Is equal to, now the current going out has got to equal to the current coming in, right? Equal to 20 milliamps. Any questions about that one? VA minus VB over 3K is equal to, or plus, VA minus 0 over 1.5K. So current going this way, current going this way, current going this way is equal to the current coming in. Or you could have written it the other way. You could have said the current coming in is equal to the current going out. That's what that is. Any questions? What's the other equation? What's the other, the right around VB? So now you're going to be writing the current going in. This is at VA. And VB, what are you going to write at VB? Well, the current going out is going like that, and it's 20 milliamps. And the current coming in this way is VA minus VB. And the current going out this way is VB over 2K. And the current going out this way is VB minus 0. So basically you can write that one. So you can say the current going in is VA minus VB over 3K plus VB over 1 plus 1 is 2K. That's the current going that way. Current going down this way is plus VB over 6K. And that is equal to the current going, oh, excuse me. Current going in, current going, okay, I got it wrong. Current going in is equal to the, okay, I'm going to do this again. Okay, so the current going in is this one right here. And that is equal to, whoops, I got the wrong flavor. It's equal to the current going in is equal to the current going out. So current going in is VA minus VB, okay, over 3K. Current going out is VB over 6K plus VB over 2K plus 20 milliamps. Now, we've got to get, to find VA and VB, we've got to get the VAs and the VBs on the left side and the constants on the other side. So in order to do that, we basically have to say, okay, it's VA, this is called standard form over 3K, plus, excuse me, plus, okay, I'm slow today. I don't know why, but I am very slow. Right? VA times, I'm working on this equation right here, 1 over 3K plus 1 over 1.5K plus VB times minus 1 over 3K is equal to 20 milliamps. Then the other equation is VA times 1 over 3K plus VB times minus 1 over 3K, which is that one, minus 1 over 6K, which is that one, minus 1 over 2K, which is that one, is equal to 20 milliamps. Oh, and up here it's minus 20 milliamps because it's 20 milliamps minus 40 milliamps is a minus 20 milliamps. I missed that. Okay, so now I've got two equations and two unknowns. Now I've got a mess because this is all denominators, and that's why node equations are so difficult to work with. Now I come back up here and erase the top part because I got to use that area in order to build this all up. So I got to now go back up to the top and start building this up. Or else I can just, what I can do is I can just expand this. I'll just expand this. Okay, so that's mine. All right, so now let's go back and make this bigger. Oh boy, how do I expand this? I expand this out to make it the whole size of the whole thing. I don't know. I don't know how to make it bigger. Window. Well, let's just. Anybody know how to do that?
You might have to put a cursor on.
Say again?
See how there's like a little cursor on the merge selection? Might have to put it on
On this?
there. Yeah, maybe.
Well,
a little right there.
Scale, rotate scale. Okay, well. Well, I tell you what I want to do is I'm just going to write that over and then tell you what I'm going to do is I'm going to write it over and then I'm going to do the whole page. I don't really know how to do this really quickly. I'm sorry I'm a little bumbly this morning, but most of everybody it just takes a while to get going with these. Okay, so let's just go back to this one here and put it right over bias. Right there and get this as big as we can. Okay, so let's just get it as big as we can. I don't do that. Okay, so let's just do it as big as we can, and then that'll maybe work as to our. All right, so say it again. Okay. So it's VA. The current going out. These are hard. These are not easy. So it's the current going out of 40 milliamps plus VA over 1.5K plus VB or VA minus VB over 3K. That's current going out, current going out, current going out is equal to 20 milliamps, or the current going in. The other one is current going in is VA minus VB over 3K is equal to, current going in is equal to VB over 1K, or excuse me, 6K, which is that guy right there, plus VB over 2K plus 20 milliamps. All right, so that's current going in, VA minus VB is equal to current going out is this, this, and this. Okay, so now let's rearrange this. Standard form, VA times 1 over 1.5K plus 1 over 3K plus VB minus 1 over 3K is equal to minus 20 milliamps. That's our first standard form. Second standard form is VA 1 over 3K plus VB minus 1 over 3K minus 1 over 6K minus 1 over 2K is equal to 20 milliamps. Okay, so here's the first one. Here's the second one, all right? So, now these are small numbers. We have to go through and just do calculations to get these. VA over 3K minus, minus, and that. Okay, so now let's take our calculator and get these numbers. So it's VA one divided by 1,500 plus 1 divided by 3,000 equals, or 0.001. So it's VA times 0.001 right there, plus VB times 1 divided by 3,000, or 0.000333, minus 0.000333 is equal to minus 0.020. Okay? Now, eventually we can go through and we can multiply everything by 1,000 and we can get rid of all these small numbers. But right now we've got to deal with it. Okay? So VA is the second one. Here's my first one. Here's my second one. VA over 1 over, point 0.000333, and that's that one, plus VB, okay, and now it's 1 over 3,000 plus 1 divided by 6,000 plus 1 divided by 2,000 equal. So that's 0.001, okay. Is equal to 0.020, okay? So, 1 divided by 3,000. Yeah. Okay, so now we have these numbers. And now we have to arrange these numbers so that we can find our answer. So VA is equal to the determinant. In this case, we use these numbers over here, minus 0.020 and 0.020. And then we use these numbers in our other column. It's minus 0.000333 minus 0.001, and that's our determinant in the numerator. Our determinant in the denominator is just these, 0.001, 0.000333 minus 0.00033 and minus 0.001, okay? And then the cross multiplication gets you your answer, so it's this times this minus this times this. So let's practice and do that once. Everybody find that. It's minus 0.020 times minus 0.001 minus 0.020 times minus 0.00333, okay? Practice and see if you can get the right answer. This is where it gets fun. Minus 0.020 times minus 0.001 minus 0.020 times minus 0.000333 is equal to what? What do you get? I get 0.000266. Is that what everybody got? Did you get that?
Yeah.
Anybody else? Did everybody follow what I did? Okay, now the denominator. It's this minus this. So it's 0.001 times minus 0.001 minus 0.000333 times minus 0.000333 equals I get minus 0.00000889 I get 6 zeros. 1, 2, 3, 4, 5, 6. Okay, is that what you got? Is that what you got? Now you divide. And this is a mess because these are so small numbers. If you want to, you can at this point in time up here move everything, multiply everything by 1,000. It makes it a lot easier, okay? And I didn't do that because I didn't want to show you any tricks, but this is how you do it. 0.00002666 divided by minus 0.0000008891 equals 29.98. Or about 30 volts. Minus. Okay. Now everybody see how to do that? Everybody see how messy that is? Have you done this before? Never in your life done this before? Some of you have, some of you haven't. Now, do you know how to do this? Could you do this on a test? Yeah. Again, you've got a crib sheet, you can do this on a test. Now, how do you find VB? Same way. VB is, instead of this, it is, with VB, it's used, so for VB, it's minus 0.020, but then on the, excuse me, I'm sorry. I got the stuff on the wrong side. Okay, so I got to go back and do it again. Let's just do that. VB is equal to 0.001, 0.000333, but then on the right side you use the minus 0.020 and the 0.020, and that's your numerator. The denominator stays the same. So once you calculated the denominator, you keep it the same, but the numerator, you move, for VB, you move your right side into the right column. For your VA, you move your right side into your left column, and this is called Kramer's rule. And welcome to matrix algebra. That's how that's done. That's all that you do. That's it. It's a way to find VA and VB with two equations, two unknowns. Okay. Now, these are messy. I don't like them. Nobody likes them, but you need to know how to do them, okay? But again, would I ever ask one of these on a test? I doubt it, but I don't know. I'm not going to promise you no. Here's 3.4, which is the other one. I got two of these. Did everybody get this one? Did everybody get it that wanted it? Okay. Okay, so 3, 4. This is the other one that I ask you to do of this kind. So this is, again, so you look at it and you say, okay, now you write it around VA. What's different about this one and the other one? This one had, the other one had two current supplies in it, didn't it? This one has a current supply and a voltage supply. So that, this one has how many equations? How many unknown voltages?
3.
3. So it's a 3 by 3. And this is a little bit messier, but it's the same basic process. Okay, so basically this one is 3 equations. So around VA, I say at VA, we have what? What's coming in? 10, right? 10 milliamps is coming in is equal to what? Going out? VA over 4K, and that's this one going down. What is it going this way? Plus VA minus 5, because it's at 5 volts right there at VB. We really don't need VB, do we? VB is, we know VB. VB is 5, so we really don't have to write an equation at that. So basically, we have still 2 equations to unknowns. Okay? So VB is 5. So it's VA minus 5 over what? 4K. And that's it. Okay? Now, here, we can write VB, but we don't have to. We can just say 5. So VB is equal to 5. Now, at this point, VC, we can write, we don't have to write VB at all, because VB is equal to 5 volts. Over here, we have another voltage, which is called VC, and it's the only thing we got. That's the only other known voltage. At VC, we have what? What's going in? 5 minus 4K. So what's going in is this right here. It's going left or right. So what's going in is 5 minus VC over 4K. And that's what's going in is equal to what's going out is equal to 10 milliamps plus what? What's going out this way? VC over 4K, right? And we're done. Really, this is really 2 equations to unknowns. I said it was 3, it's really 2. Because VB is 5. We don't really need to write VB, okay? So what do? Same thing we did before. It's called sorting and sifting. So on the left is the VA or whatever. So on the left is VA times 1 over 4K plus 1 over 4K. Okay, period. Plus VC times what? 0. Equals, now I'm shifting the left to the right and the right to the left. I hope you understand that. Is equal to what? 5 over 4K plus 10 milliamps, or 0.010. Okay? Everybody understand that? So I got my 10 milliamps over here. I shift this over there because it's a constant. And there's no VC in this equation, so you say VC times 0. So I've got my VA times this. And then I've got my VC times 0, and I got this on the right-hand side. Now that's my first equation. What's my second equation? This one is only VC, so basically I can find VA and VC because the other one is 0 in both cases, and you don't really need, in this case, you don't need, it solves itself because VA is the only thing in this equation, VC is 0. In the second equation, VC is the only thing, and VA is gone. So really, we don't need to do 2 equations to unknowns. We just need to solve for that various. Follow me? That's it. So in this case, VA is going to be 5 over 4K plus 0.010 divided by this. VC, we got VA times 0 up here. And the second equation is equal to what? VC times minus 1 over 4K minus, excuse me, and I got minus 1 over 4K minus 1 over 4K is equal to, And that's everything on the, I shift everything to the left for the VC and everything to the right. So it's equal to 10 milliamps minus 5 over 4K. And that's my VC. And you can find the answer there. And that's not hard. This one falls apart because, first of all, it's symmetric and the VB is given. If there was a resistor here instead of a voltage supply, this one would be as hard as the other one. It would be a 3 by 3. But because we have VB given as a 5, it falls apart and we have a very straightforward answer. Okay, that's 3.4. These are messy. I can't say I won't give you one of these on a test. I want you to try them, but daggone it, these are kind of like painful to the extent. Okay, so let's just keep on going. Then 3.9. Sorry I bring you into all this stuff, but my opinion is that, okay, now this one is formulate node voltage equations for this one. This is another one. And this one is what? How many unknown nodes are there here? Well, there's this one. This one we know. This one we don't know, and this one we don't know. So really this is VA and VB. So this one we know, this one we don't know, this one we don't know. So we're going to write two equations, two unknowns for this one. This one's a little bit more, I don't know, just a little bit more than the other ones. Let's just try it though. This is 3.9. So with 3.9, we have, so this is going to be my VA and this is going to be my VB. Okay, so VA, so for VA we say, no, yeah, I guess we can. We can write this, here's an unknown and here's an unknown. This one is known. This could be VA, but it is minus 30, by the way. If this is ground, if this is 0 volts right here, this is minus 30, okay? These are strange problems. They do strange things to you, but this is basically minus 30. So basically, this is my VA right there in the middle, and you write around that when you say what? Now, is the current going in or the current going out? I don't really care. So at VA, we have a current going in, and we have a current going out, and we have a current going out. And I'm going to define it like that. It's going to be, and it may be backwards, but I'm going to say minus 30 divided by 10K is my current going in. Does everybody follow that? My current going in is this voltage minus VA, and this is minus 30 minus VA over 10K. So minus 30 minus VA, so it's this voltage, this would be a voltage minus VA over 10K is the current going in. Now the current going out is VA divided by 15. VA divided by 15K plus VA, this is VA, minus VB over, excuse me, it would be VB plus 10. No, VA minus VB is 10. Okay, so it's VA A minus VB is 10. This is equal to 10, so we really know that already. So the equation for this one is current going in here is that. But now the current going in here is we don't know the current. We don't know the current of this node. So we do know the current here. This one is we can't write this equation for this one at VA because we don't know the current going in here. We can write it for here, however, and let's do that. This one's not easy. This one's I didn't see this, but this is not an easy one at all. This one is a I tell you what. I'll come back to this one because this one's not. I may do it again sometime, but I'm not going to worry about it right now. I'm going to work on that one. I'm not going to try to get that one. Skip 3.9. All right. New. Let's go to 3.11. Now this one is not so bad. All right. This one isn't so bad. 3.11. So for this one, we basically are doing current. This is mesh. All right? And with mesh analysis, we define a loop and another loop, and we just start writing. So we usually start lower left-hand corner, and if we come up, we run into a voltage supply. If it's a minus we run into, we write minus. If it's a plus we run into, we write plus. So we write minus 5 plus 3.3K times IA plus 2K times IA plus. Now over here it's IA minus IB, so it is IA minus IB times 3.3K. And do I write this as a minus or a plus? I write it as a minus. Equals 0. So I've got 3K. I said minus 5, 3.3K times IA, 2K times IA, 3.3K times IA minus IB minus 5 equals 0. Over here, I write, start lower left-hand corner, I write what? Plus 5 plus IB minus IA times 3.3K. That's that one right there. Plus 2K times IB plus 3.3K times IB plus 5 equals 0. Find IA and IB. It's sorting and sifting is all it is. So here you've got IA times 3.3, that's that one, plus 2, that's that one, plus 3.3K, and that's that one, plus IB times minus 3.3K. All right? That's that one right there. Equal 10. Second equation, IA times minus 3.3K. See how much easier these are? Plus IB times 3.3K plus 2K plus 3.3K equal minus 10. All right, now, what we have now is 6.6, 8.6, IA times 8.6K plus IB times minus 3.3K equals 10. Second equation, IA times minus 3.3K plus IB times 8.6K equals 10. Minus 10, excuse me. Solve. IA is equal to 10, 10 minus 10 minus 3.3K, 8.6K. That's my determinant in the numerator. My denominator is 8.6 minus 3.3 minus 3.3 and 8.6. So there it is. It's 8.6 minus 3.3 minus 3.3 and 8.6. And let's do that and find out what our answer is, and that's it. This is a lot easier, by the way. Mesh analysis is a lot easier than nodal analysis. So basically all you got to do is multiply 10 by 8.6K, 10 times 8 point, excuse me, minus 10 times 3.3. So let's do it again. 10 times 8600 minus 10 times 3300 is equal to 53,000. And the denominator is 8600 times 8600 minus 3300 times 3300 equals 6,307,000, no, 63,070,000. Okay, so let's do it again. 8,600 times 8,600 minus 3,300 times 3,300. Yeah, so it's 5,300 divided by 63,070,000 equals what? 0.000084 or 84 microamps. That's it. That's IA, and IB you do the same thing for. Mesh analysis is a lot easier. Any questions about mesh analysis? Straightforward, loop, loop, done. Okay, that's 11. Let's go down to 20. Okay, now you get into a situation where you do loop equations, but IB is by definition 20 milliamps. You see that? So you don't have to write an equation for IB because, well, IB is minus 20 milliamps, but you can write the equation, but you don't have to write, when you write IB, instead of writing IB, just write minus 20 milliamps, because IB is minus 20 milliamps. So basically, this equation becomes IA and IC. This becomes a little easier, all right? So for this one, up here, you write okay, so this would be for problem number 20. You write, I'll just say this, I know that at times it's kind of rough, and I did not go through each of these problems ahead of time, I will have to go back and do some of them again. Some of them, when we get into the longer ones, and these are not the longer ones, these are some of the shorter ones, I'll have to go through ahead of time to an extent, but I am not able to, this is my first time through this book, to just go through every one of these and have them 100% ready for you. I'm sorry, but I don't have time. And I'm apologizing already for what I know is going to be an interesting semester, but I get through them. We'll get through them. But so this one basically is you're writing an equation for IA and IC. IB is equal to minus 20 milliamps. So when you get to IB, you just write minus 20 milliamps and you're done. All right. So let's start here and write the equation for IA. Let's write here and write IA. So it's IA times 22K plus IA minus IC, parentheses, times 47K. And then I run into the 24 volts plus on the left, so I say plus 24 plus IA minus what? A minus 20 or plus 20 milliamps. IA plus 20 milliamps times 15K equals 0. So that's writing that equation for this loop right here. Everybody see that? So this is the trick for this one. You say IB is going in this direction, but it is contrary to this. So basically what you say is IB is equal to a minus 20 milliamps. So when you say IB, you don't write IB to say minus a minus 20 milliamps. So it's IA minus a minus 20 or IA plus 20 milliamps, and you're done. The other equation, the IC equation is what? Start right here. IC, said the blind man, IC times 33K plus or minus a minus 24 volts, because I ran into it from the minus side, plus IC minus IA times what? 47K equals 0. Now, you solve for IA and IC and you're done. Okay, so IA, 22K. I put a check mark when I see it, 47K. $15K. That gets that one. All right, so that gets me my IAs. What about my ICs? There's an IC minus 47K. What about my, on the right-hand side? 24 minus 24. And then 0.020 times 15,000 is what? 20 times 15 is 30. It's a minus, so it will be a plus over here. It'll be a plus 30. So 0.020 times 15K is 30. So, and it's a minus, excuse me, it's a plus over here. It's a plus here, Ted, so it's a minus over here. It's a minus. That's a minus. Minus 24 minus 30. Okay, so that's a minus sign. If anybody doesn't believe me, I'll do it again. Right, minus 30. So it's a plus 20 times 15K, 0.020. That's 200, that's 300, excuse me. It's 20 times 15 is not 30, it's 300. Okay, so that's right, 300. All right, so that's my answer on the right-hand side. So 0.020 times 15,000. 0.020 Yep. I knew it was right, but I just missed it. So minus 24, minus 300 over here, and now I've got my two equations, okay? Or I got my, um, this is the first equation. Now my second equation would be IA times minus 47K, that's that one right there, plus IC, and IC has to be plus 33K plus 47K, that's that one, equal 24, right? I'm done. Except I got to now go through and evaluate it. And that's all I got to do is IA is equal to um, minus 324, and then 24, and then minus 47K, and then 33 plus 47 is 80K. The numerator and the denominator is 22 plus 47 plus 15. 84. 84K minus 47K minus 47K and 80K. All right, so you evaluate those and you're done. This times this minus this times this over this times this times this times this. Anybody want to crank through that and do it? Find my IA, what it is? Numerator is minus 2479200. 24,792,000, and then the denominator is 84,000 times 80,000 minus 47,000 times 47,000, or 451100000. So it's wait, scratch the zeros, it's 24,792 divided by 4511000 equals 54.9 milliamps minus 54.95 milliamps. And there we have it. Not fun, but very doable. This one is very doable. Okay, so we're down through 20, and I knew we were not going to get through all these, but I'll go back and work 11, because 11 is the painful one. Okay. And these will not be due until we get through this chapter, okay? So we'll work on these a little bit more and work on them until we get them. Now, is this going to help you or hurt you with the stuff that's coming later? The mesh we'll do a little bit. We're not going to do a lot. And then the Thevenin, we'll do a little bit with Thevenin. That's the other two that we have, 58, 41, 58, and 61 are Thevenin. We want to do a little bit of Thevenin as well. Take care. If you have your problems done from chapter 2, good. If you don't, and then I'll scratch 11 and I'll rework 20. Okay, take care.